Hello everyone. In this video we're going to continue on with lesson 11, which talks about ANOVA. And so in the last video we sort of gave an introduction to ANOVA and a motivating example that hopefully helps us try to understand what's going on here. All right, and so in this video, starting actually right now, we're going to go through the steps of a hypothesis test doing the ANOVA. Okay, the ANOVA stands for analysis of variance. Okay, so we're analyzing variances, which is what we talked a lot about in the last video. So the overall goal of an ANOVA model is to compare the means of several groups, usually more than 3, but it's applicable from 2 on. Right? So suppose that we have P groups. Okay, so P is like a variable thing. I could have one group. I could have 2 groups, 3 groups, 4 groups, so on and so forth. The ANOVA hypotheses are this. Okay, so we're back to symbols and not words for our hypotheses, at least partly. Okay, we had words for lesson 10. We're back to symbol-ish type of things here in lesson 11. The null hypothesis is that all of the groups are equal. All of the group means are equal. So mu1 is equal to mu2 all the way up to mu p. Okay. The alternative hypothesis I could write in symbols like this, okay, which is probably pretty confusing. Mu sub I does not equal mu sub j for some I which is not equal to j, where both I and j are in the set 1 to p. Okay, I know that's much too much for us. What I want you to write is that at least 2 of the population means are different. Okay, so that's what that means in words. The null hypothesis is that they're all the same. I need you to write symbols for that. Okay. The alternative hypothesis is that at least 2 of the means are different. Okay. So what this test is going to tell us is that is there a difference? Is that if there is a difference between at least 2 of the means in all of my groups, then it's going to say, yes, there is a difference. All right? All right, so those are the hypotheses. The significance level is the same thing as always, and so I skipped over it here, but that's still in there. The assumptions of this test are, again, slightly different than what we've seen before because they have their own thing. The assumptions are that 1, each group is normally distributed. Okay? So if I go back to an example that I used in the last video, I could be trying to compare 4 groups to see which has the highest GPA. Freshmen, sophomores, juniors, or seniors, and maybe I'll throw in super seniors in college. Okay, so which ones on average have the best GPA? The assumption is that each of those populations are normally distributed, okay, or that there's a normal distribution of GPAs for freshmen, for sophomores, for juniors, for seniors, and for super seniors. Okay, so that's the first assumption. The second assumption that you usually see go along with the first is that each of those populations has a common variance. What that means is that each group is spread out about the same. Okay, so that there's not one group that has a really large standard deviation and then there's another group that has a really small standard deviation. Okay, they need to have similar ones. Okay, so that's what number 2 says. And then 3 was the one that we always see. The samples were obtained randomly. And so here I say obtained using randomization. It's the same thing that I've been saying throughout. All right, so those are the assumptions. Now we get to the test statistic. And just like the chi-squared, this test statistic is slightly different okay, than the rest. So the test statistic here is between group variation divided by within group variation. So again, those are words and not numbers, which may make you uncomfortable, and I understand. There are actual numbers that will go there eventually. Okay, but we don't really need to think about how to calculate those. The software that we're going to use, or that I'm going to give you output from, is going to give you these numbers. Okay. Now, we'll forget the actual numbers that go into there, and we'll look at the test statistic, okay, which is F, and its distribution. So just like in lesson 10, when we talked about the distribution for that chi-squared statistic, okay, or that test statistic for the test for association, it had a chi-squared distribution. This test statistic here has an F distribution, and an F distribution. So again, I'm introducing another mathematical model that's used to describe a situation. Okay? So now I'm describing a situation with what's called an F distribution. The F distribution is going to be a lot like the chi-squared distribution. The larger the F value, the more evidence for the alternative hypothesis. So we'll always use software for the computation of the test statistic and the p-value. Right? So here is again a short slide on what an F distribution is and sort of what it looks like. So F distribution, and so that should say F and not chi-squared here. The F is unimodal, again, just like everything else. It's skewed to the right, usually, okay, just like the chi-squared, and it's always positive, just like the chi-squared. All right. The F distribution is characterized by two different degrees of freedom. So we've sort of become familiar with degrees of freedom from the T and the chi-squared, but now with the F, we have two different degrees of freedom. Okay, and so when I want to denote that, I put the degrees of freedom in the subscript like I have been doing before. Okay, so an F has two different degrees of freedom. Okay, so now back to the test statistic. Next step is the p-value. Okay, p-value again is always a right-tailed test. Okay, so I'm always looking for that probability. And over here again, I have a little picture that shows you where I'd want to shade in anything if I drew a picture of the F distribution. Right? So the F distribution that I'd put into StatCrunch to do the p-value calculation, if I didn't have software do the whole test for you, okay, would be and the F calculator with these two degrees of freedom. Okay, so I have P, the number of groups, and I have N, which is the total sample size of all groups. The first degrees of freedom is the number of groups minus 1, and then the second of degrees of freedom is the total sample size, N, minus the number of groups. Okay, so I know this is a lot of stuff that I'm throwing at you. Hopefully you can sort of digest it, get through it enough to understand what's going on, okay, and in order to do an example problem. Okay, so that's the F distribution that we use in the p-value calculation. Again, we make the same decision, or we make a decision in the same way as we did before. If the p-value is less than alpha, we reject the null hypothesis. Otherwise, we fail to reject the null hypothesis. And the conclusion says this. Okay, and so this is sort of unique to this test. Okay, the conclusion should look like this. Every single time, the only thing that's going to change is your is/isn't, okay, enough evidence, and the significance level with which you do the test at. Okay, At the blank percent significance level, there either is or isn't enough evidence to conclude that at least two of the population means are different. You should write it exactly like that every time. Okay. Now, that's a hypothesis test. And there's one thing that I want to go back and talk more about, which are the assumptions. Okay, the assumptions that each group is normally distributed and has a common variance. Okay, we can't really, we don't have the tools right now to look at that common variance assumption, but I'm going to show you how we can actually check whether the group may or may not have a normal distribution, okay, as a population distribution. And how we do that is with a graphical method called a QQ plot. Okay, a QQ plot. A QQ plot is going to plot some points, okay, and that's going to draw a line through it in some way. And if those points are quote unquote closely clustered to the line and there are no apparent patterns, then we can assume normality. Okay? So I'll show you two examples, one where the assumption of normality is okay and one where it isn't okay. Here's the first one where the assumption of normality is okay. If you look at the plot, you'll see that most of the points are very close to the line, okay, or closely clustered to the line. And there doesn't seem to be any pattern going on in the data. This is what a good normal QQ plot should look like. And if it doesn't look like this, okay, if it looks much more weird than this, then the assumption is not okay. Okay, so that's a good one. Here's a bad one. Okay, so here's a bad one. You'll see that there are a lot of points which don't follow the red line. Okay, you'll see most of the points in here do follow fairly closely, but not all of them. Also, there is some sort of apparent pattern here. The points don't really follow a line. They kind of make a very weak U shape. So you'll see that it starts, the line keeps going down. This point starts way above. It comes down. Here it's now below, and then we're going back up. So it makes a sort of U shape around that line. This is an example of a bad QQ plot, okay, or a QQ plot where that normality assumption isn't really met. Okay, so we can use QQ plots to assess that assumption. So I'll go through an example quickly here of performing an ANOVA, and then we'll actually test. We'll get to look at the QQ plots and see whether or not that normality assumption is valid to make. So I have 5 different groups here. I call sample 1 through sample 5. I'm not going to give you the actual points. Okay, I'll just show you the picture, and I don't really also give any context to the samples. They really have no meaning. They're just numbers that I made up randomly. Okay. But I want to compare, I want to see if these groups are different. Okay. If there is a difference. And so I can use an ANOVA to do that. If you look at this picture and you just sort of try to reason through and see what the ANOVA might say about this, you'll see that sample 1 and sample 2 look very similar. Okay, and sample 4 and sample 5 look pretty similar. They do look slightly above sample 1 and sample 2. And so I'd probably say there's a difference there. And then we have sample 3, which is a lot larger than any of the other samples. So we should, based on this picture, we should believe, or we shouldn't be surprised when there is a difference between the groups. Okay? So, level of significance we'll set at 0.05, just to be not fancy. Okay? And then we'll start off with the hypotheses. There are 5 groups. Okay, and so the null hypothesis are that all of the 5 means are equal. And the alternative hypothesis is that at least 2 of the population means are different. Okay, assumptions. Here are the 5 QQ plots. And if you look at them, they all seem to be fairly closely clustered to the line, and there are no apparent patterns. You may say, well, that doesn't quite look like it in this top left plot, and maybe you could argue in this bottom right one. And that would be a fairly good argument, but it turns out that these are still okay. Okay, so it has to be more heinous than these 2 in order for me to reject that. Okay, so all of the assumptions, the normal assumption looks great. Okay, equality of variance, we can actually look at some things, but I'm not going to make you in this class. This is actually from another more upper division course than the one you're taking right now. It looks like they're spread out about the same. Okay, there's nothing really different there. Great. And then are the samples taken randomly? Yes. Okay, so they are. So all my assumptions are met. I can move forward to the test statistic. Okay, and so here's the ANOVA output. Okay, this is what you'll see no matter what type of software that you use, Minitab, StatCrunch. This is R. Okay, it's going to look like this. All right, and there are a lot of numbers here. Okay, a lot of numbers here. Some of them represent between group variation, and some of them represent in group variation, within group variation. But you'll notice that here is the F value. So you see this right here. This is your test statistic. And then here is the p-value. So our test statistic is 41.02, which is very large. The p-value is very small. So I reject the null hypothesis. And my conclusion is this: at the 5% significance level, there is enough evidence to conclude that that at least 2 of the population means are different. Okay, and so that is an ANOVA hypothesis test. Okay, now something that I want to point out is a little bit about the calculations of the ANOVA table. So again, here's that same output. And side note, I'm doing this because your homework asks you to go through and talk about the ANOVA using this ANOVA output type thing here. And so I want to make sure that you understand all of it. So some of the important parts that the degrees of freedom for what they call the sample, okay, which are all the groups, is the number of groups minus 1. Okay, so here's the number of groups minus 1. Down here, 95 is the total sample size minus the number of groups, okay, which is the second degrees of freedom thing here. Okay, 95, there were 100 samples, 100 points, 5 groups. So 100 minus 5, 95. The sum of squares we don't need to worry about. These mean square numbers are actually the sum of squares, this number, divided by the degrees of freedom. So this number here is actually this number divided by this number. And this group, this value here is this divided by this. Okay, the mean squares. How do I get the F value? That's the especially important part. the f value is actually this mean square divided by this mean square. Okay, so to get this, I take 347.2 divided by 8.5, and I get that. Okay, then I can compare to the f statistic with 4 and 95 degrees of freedom to get my p-value, so on and so forth. Okay, but you'll need to pay special attention to these things that are going to help you with the homework. Now, the last thing I want to talk about in this video is something that doesn't quite sit right when you're done with an ANOVA test. Okay, the ANOVA test that we performed before checking before the ANOVA output type stuff is what I call an overall test. Okay, and I say it's an overall test because I had 5 groups and it told me that at least 2 were different, but it didn't tell me which of those 2 were different. Okay, 2 or more were different. It only told me that there was a difference. So what we're going to do is we're going to use some more methods called a multiple comparison method. Okay, so to look at the pairwise group differences, we're going to use a multiple comparisons procedure. It's going to be like doing some things that we haven't done in this course called 2 sample t-tests, but with a few key differences. Okay, and then I write here just a little bit about what a multiple comparison procedure is. I'll let you read that, okay, and we'll move forward. Okay, the one that we're going to use is called Tukey's HSD. The HSD stands for honestly significant difference. This is what Tukey's HSD looks like. Okay, or this is the output that you'll be presented that I want you to read, right, and respond to. So here they give you a bunch of information. All of it's important, but only some of it is important to us. Okay, they have each of the different, so they compare each of the different groups. So they compared 2 to 1, 3 to 1, 4 to 1, 5 to 1, 3 to 2, 4 to 2, 5 to 2, 3 and 4, 3 and 5, and 4 and 5. Okay, so they looked at all possible group differences, and what they give you is a confidence interval and a hypothesis test p-value. Okay, and so with these, you can make a decision about which groups are different from one another. And so if you look at the p-value and the confidence interval together, okay, you'll see that group 3 is different than all other groups, which, if we think all the way back to the picture, makes sense. Okay, 3 looked a lot larger. The average looked a lot larger than the other groups. And so if you look through at the second line, the p-value is 0. And if you look at the confidence interval with lower and upper bound, you'll see that 0 is not contained in the interval. If 0 is contained, then there is no group, there is no difference. If 0 is not contained, then there is a difference. And so if you go through down here, you'll see that anytime you see a group 3, you'll see 0 is not included. Okay, 3 is different than all other groups. 4 is also different than 2, okay, at the 5% significance level there. Okay, and 5 is different from 1 and 2. Okay, so if you go through and look at the p-values or look at the hypothesis tests, all of these here that I talk about in the bottom left show out in either the confidence interval or the p-value. All right, to do these, okay, or make some statement about these in the homework.